introduction. All right, it's my pleasure to be here. I am going to talk about a few recent works that I think would be a nice place to start our journey. But before I talk about the actual technical work that we did, I want to just set the stage a little bit. So for today's talk, I want to discuss robot models that are trained on data like this. You get a sequence of observations. This typically consists of some proprioceptive states of the robot, plus some high-dimensional observations, let's say like RGB images, and corresponding actions of the robot. And with this data, you can train very broadly two kinds of predictive models. The first kind of predictive model looks something like this. You get to see a history of observations, and you learn to predict some future actions. This is maybe commonly known to all of you as some kind of like behavior cloning policy or imitation learned policy. It's become very popular in the past few years. Here's just two examples, diffusion policy and Pi0, that are trained essentially like this. But another kind of predictive model you might seek to train with this kind of data is something like this. You get a history of observations, you get future actions you want to take, and you're trying to predict the corresponding future observations. This might be known to you as something like a world model. There's a lot of work as well in academia on this. There's some old papers like Dreamer you might know of, some recent papers like Dino World Model. And these days it has also become very popular for companies as well. So maybe some of you have seen NVIDIA's Cosmos, Meta's VJEPA 2, 1X Technologies World Model. So this is just a different kind of model you can train with this flavor of data set. And so the question I want to talk about today is how do we detect out of distribution scenarios in models like these? So you trained on some kind of data set of observation action pairs, you now deploy, you get to see some real observations, or maybe you're taking some actions. And the question is, okay, what's your model going to do? What's your predictor going to do? And just super broadly, so we're on the same page, I'll mention like three classes of popular OOD methods today. There are many, many more than this, but these are the ones I just want to quickly highlight because they're quite modern and relevant to many of you in the audience. So one is something like you look at embedding distances between your training data and your deployment data. For example, something like cosine similarity between an embedding of an observation you see in your data set and an embedding of some observation you see at deployment time. Oh no, if they're too different, you're probably in some OOD condition. Another is to use actually foundation models. You have them analyze the deployment data to figure out if there's important features that are anomalous or strange or out of distribution. And another one that's quite popular, so there's actually some work here at RSS from Toyota Research Institute, where you might train something like a density estimator or an energy-based model, and in low density regions, you say, uh-oh, I'm in some kind of out of distribution. The key thing I want to talk to you all about is the detection of OOD events, that while there are several methods you can choose from, there's still more to be done. But what I really want to talk about today is what should a robot do once it detects an OOD condition? And so in this talk, I want to talk a little bit about going from detection to mitigation of OOD conditions. And I'm going to talk about two works. These are both very recent works. We just put them up on our archive from my group because only the freshest and hottest things for all of you guys. One is focused on the world model paradigm. What does it mean for us to control away from OOD failures when you're relying on this kind of model? And the other is the behavior cloning or the imitation learning paradigm OOD detection. So we'll talk about that in the second half. Okay, let's start with the world model scenario. Okay, so let me just take a quick poll. How many of you know what a world model is? Raise your hand. Wow, I'm preaching to the choir. Very good. Okay, so I can zoom through the kind of setup of how these work, but just so we're on the same page, because many people mean different things when they say world model, I'm gonna do a little intro here. Now, why do I think these models are interesting? I think they're interesting because when you start to deploy robots, especially interactive robots, like let's say manipulators that have to physically interact with the environment, there's some excitement that these kinds of models could potentially help us predict consequences of interaction that are really hard to model via first principles representations. For example, so this is a recent demo. How many of you have seen this demo from Generalist? Okay, so it came out pretty recently. Yeah, I think it's really cool. Like they're pouring these brews into a little container. This is not, to my knowledge, using a world model, but I think it's a really nice interactive example where, for example, cognitive scientists would talk about the intuitive physics we have in our brains to understand how this is going to fall out. So I think that's really cool. There's a lot of other examples that are not robotics here of really interesting, complex failure modes and interactions. And on the right-hand side, we're going to use this as a running example in some of the early parts of today's talk, which is a robot interacting with this deformable filled Skittles bag. Okay, so to actually obtain a world model, I told you that this is the data we use. Just a really quick summary of how these generally are structured. You do something like this. Okay, you take your observations, you have some encoder. This encoder can be co-trained, it can be pre-trained, and this essentially does some dimensionality reduction. It gets you a latent state vector Z. And then what you do is your latent dynamics model or your world model is learning some transition function that takes this input in action, your current latent state, and predicts some next latent state. And you can train this via a variety of objectives. Oftentimes these are self-supervised. So for example, you know the next observation. Maybe what you can do is you can say, well, the next predicted encoding should be really good at predicting the actual images. So I use some pixel level reconstruction, but there's many, many flavors of this, and you should check out foundational works for precisely how you do this. In fact, I'd argue there's a lot of exciting work to be done on how you even learn these models in the first place. But this, from a mathematical abstraction perspective, is kind of where we're at. So again, to reinforce why I like these models, I think it's very exciting because it can help robots learn really hard to model state and dynamics, like those interactive tasks I showed you before. And once you have a model of the world that's very hard for you to write down, in fact, also very hard for you to simulate. My student tried very, very hard to use Isaac Gym to simulate a deformable bag. It does not work very well right now. Okay, so once I have a model, then I can also start doing control. And I can actually come up with control strategies that keep me away from these things that are, I know them when I see them, but I don't know how to write them down. And this is precisely what we were presenting here at RSS, some first steps towards this direction. So here the idea is, this gray blob here is your latent space learned by your world model. Some subset of that state space corresponds to, let's say, bad outcomes, things that you have seen that you definitely never want to see again. So in our case here, it's like this spilling failure, right? Like the Skittles have fallen out. This is your constraint. And you and I know that if I show you an image of this spill, you can detect that it's bad. So what we do is we learn a classifier here that can essentially detect just from the latent states which of these would look like failures by essentially just posing a classification problem in the embedding space. So now that I know what looks bad, I'm going to try to make sure I never do this again. So I want to be super clear. We have to see a little bit of this. We have to see a little bit of bad outcomes because I can't control, I can't predict. But once I figure this out, what we do is we solve something called a reachability problem in the imagination of this world model. And really intuitively, what we're essentially trying to obtain are these inevitable failure states. Something like this. The robot, imagine, is teleported into the situation. It's grabbing the Skittles bag like this. No matter what it does, those Skittles are going to fall out. I can't see them right now, but they are doomed to come out. And this is an inevitable failure state I need to always avoid. And so formally, what we do is we solve this kind of safety critical control problem, but all within the imagination of this world. And if some of you attended my student Ken's talk, you'll see that what we can do is we can just kind of zero shot apply this world model, the safe controller, which takes as input directly these observations to shield a teleoperator from ever making a decision that would be doomed to spill those Skittles. So, if you're grabbing the Skittles back from the bottom and trying to pull up, the safety controller stops you. If you're sliding side to side, it slows you down. And we stress test this a little bit, it's an OOD workshop. We stress tested this a little bit. And the safety controller is generally reasonable at performing in small OOD conditions. For example, we changed the Skittles bag. I couldn't find all the flavors of Skittles in Pittsburgh. I found as many as I could. We tried to change the background color, and it doesn't totally fail. So for example, it'll constantly block those teleoperator controls that are trying to pull up the bags. But there's still more challenges. So in practice, when I'm building this predictive model of the world, it's really hard to get coverage of all possible failures and all possible outcomes. In fact, I probably don't want to see every single bad thing ever. How many of you have played Jenga before? Raise your hand. Amazing. Okay, I too love Jenga. I bet that all of you have not seen every single possible way in which a Jenga tower falls. Maybe you have, maybe you love Jenga that much, I don't know. But you still kind of understand that if something weird is gonna happen, I probably should stop pulling out this block. Now, if we just deployed that safety filter paradigm that I just talked about in this kind of Jenga setting, the problem is that when you start to interact with the world in new ways, the imaginations can sometimes be unfaithful. So for instance, here, the robot is pulling out this block, and you see the real outcomes on the top, the imaginations on the bottom, and you see that the robot's actually quite optimistic about the outcomes of how the block is going to interact. And it's because it's never seen these combinations of the block tower interacting. We're in an extremely low data regime, by the way. And this leads to our safety critical control being kind of compromised. And I want to also have a quick note. This phenomenon is still also kind of present at scale too. How many of you know of the company 1X? Raise your hand. Okay, 1X has invested a lot in world models. Here's an example from the recent paper. This is the real trajectory of like the humanoid hand interacting with this plant. This is in the paper. This is the imagined outcome. So the plant kind of ducks. Okay, so this is still an open problem in world modeling, period. So what we were asking ourselves is, okay, if we go back to our latent space safety problem, there's some true failure set, but in reality, I'm only getting coverage of some subset of these failures. These are the ones I actually get to observe. Like, for example, maybe I've observed a little bit of how the Jenga tower falls. But there's situations where I'm going to be doing safe control. I'm going to be imagining outcomes of actions and interactions I've never ever seen before. Some of them are fine, some of them it doesn't matter, but some of them are going to lead me to new failure states I had never seen before. And so one way for us to tackle this is essentially we said, well, what if we use kind of the epistemic uncertainty of the world model itself, like how confident is it in predicting the next state, as a proxy for unseen failures. So here's an uncertain imagination, right? The robot is confident the blocks are going to fall down. Here they actually fell down. And if you actually do your uncertainty quantification, you can actually figure out that in this case, the model was not very confident about this next outcome. But we still preserve those known failures in our safety spec. So now when we say this is a failure is anytime you enter into an out of distribution imagination or you enter into a known failure state. And this work was led by my PhD student, Jun Wanseo. He's not here at this conference, but he was also working with my other student, Ken Nakamura, who is here to present a poster on this work. So I'm not going to go into the details here. The main thing here is that once you do this specification and this uncertainty quantification, you now get a safety policy that keeps you both in distribution and away from known failures. And so you get nice behavior like this here, where this robot, which is, this is another safety controller that's shielding a teleoperator. And when the teleoperator is trying to pull this cube or this block aggressively out, the safety controller keeps preventing him from doing this aggressive pull out because it knows that something weird is going to happen soon. Like it doesn't know what's going to go next. And so then the safety policy overrides. But you should please check out the workshop poster for more details on how we model the uncertainty, how we do the actual safety spec, and how we actually do the optimization. So Ken will present this poster on behalf of June. All right, so this is part one of how we go from just detecting something is weird to actually mitigating. Now let's change gears and talk about these behavior clone policies. All right, so the task I'm going to be motivating here is we're using a diffusion policy as our imitation-based learning policy. And there's a task that this robot has been trained to do, which is essentially sort organic and recycling waste. So the training distribution, it has seen M&Ms, and then it has seen these crumpled pieces of paper. And you sort the recycling at the top, and you sort the organic on the bottom. And as you can tell, it's sorted these effectively. The general success rate is pretty good. Now, what we did was we threw in other objects for it to sort into recycling or into organic waste. So Doritos and thumbtacks and napkins. And it's very confusing why the policy doesn't do the right thing. Sometimes it does the right thing, other times it doesn't. In these examples, it all sorts these incorrectly. And here's where you could go back to those basics. You could say, let's go back to OOD detection. Let's use one of these methods off the shelf to figure out, oh no, these environments are out of distribution. Something is wrong. And in fact, we did. So we looked at these embedding distance, these cosine similarity measures, for quickly detecting if one of these scenes is strange. But again, the question is, what should happen next? And again, I think it's quite tempting for a lot of us to be like, okay, I'm gonna just collect more demonstration data. I'll expand everything it knows about. This is a very low data regime. Maybe it'll just all go away. But if we look back at what the robot has learned, the robot already has a really useful capability. It knows how to do this like contact-rich task of like scooping and like, pushing objects like up and down. So it already has the correct behavior within its distribution. It doesn't understand the correct mapping. It doesn't understand that these new objects are just organic or recycling, or maybe have like very similar interaction properties. And so this is what we studied in this recent archive paper. This was led by a PhD student, Pran Gupta, who unfortunately isn't here. And the key idea here is that maybe we can actually transfer in distribution behaviors directly to these OOD conditions, as long as the in distribution, out of distribution conditions share some functional correspondences, functional similarities. And functional correspondences, by the way, are an old idea. They've been actually around in computer vision for a really long time. That was actually some of our inspiration here. So you should go check out that really nice work. And so our idea here was, how can we bring that intuition to get these visual motor policies to adapt? And so here is where we presented this method. It's called adapting by analogy. It's just a runtime observation intervention method that's going to generalize your policy from OOD conditions based on finding functionally corresponding in distribution behaviors. So we're back in this OOD example with the napkin that it has to sort. We do that fast OOD detector by a cosine similarity, like I mentioned before. So we embed this current observation. We embed, we have all the training data that's been embedded as well. And in this particular case, life is really good. Things seem pretty reasonable in our embedding space. And so we let the policy run. But then there comes a point where, for some reason, our really fast, coarse OOD detector says, uh-oh, something weird is going on here. Like the cosine similarity is too different. And here is where what we do is, first, we essentially look at the observations in our training data and in deployment time. And what we do is we semantically segment them into different regions, right? So for example, you could semantically segment into paper, background, gripper, whatever. And now what we can do is we can look at some intersection over union, some correspondence between these labeled regions of the images that we're seeing right now and the labeled images we saw at training time, and retrieve some top K, most functionally corresponding training observations as a start. So here, maybe these are the ones we retrieve. It's the M&Ms and the crumpled paper. And now what we do is, you can sample from the policy if you like plug in each of these observations and say, what would you do? And it turns out here that there's actually multiple things the policy would want to do. It still thinks that, okay, I can maybe go up and I can maybe go down. And if there are multiple behavior modes in these retrieved samples, our method then says, I still have ambiguity. I still exactly don't think I understand what the correspondence in the behavior is, because there's multiple behaviors I can retrieve. So what I'm going to do is I'm going to ask an expert. So here, the robot shows the expert the scenarios and says, okay, what correspondences do you see between the training and the test conditions? The expert says, oh, treat the tissue like a paper. This is the adapting by analogy part. This lets the robot now refine which of the observations it's retrieved. And it repeats this process until there's unimodality in the behavior that it's retrieving. So fantastic, it has figured out the correct behavior. And now what we do is, instead of passing it in the raw observations that it's seeing at deployment time, anytime this process is happening, we're taking some average embedding of all of the functionally corresponded observations here, so like some top K. So here's the overall system in action. I'm gonna be super upfront with you all. It's a slow system right now. We have not optimized this retrieval process. For example, many of you might be familiar with like retrieval augmented generation. You have to be clever from a data management perspective of how you actually do these things in robotics. The need for doing this very quickly is very important. But for us, it was a sign of life where this robot actually is able to switch between understanding things that it can just do zero shot, like no adaptation, and things that maybe it needs to kind of retrieve by prompting with these visual observations that are essentially going to elicit the correct behavior that get it to do the correct thing. And so ultimately, the robot is able to sort the trash effectively here. And so with this, what I'm going to do is I'll quickly just say you should also attend the poster session for Pranay's workshop poster as well. This will be likely represented by either my student Ken or my student Yelin, depending on their other constraints, and you can talk to them about more details as well. And with that, what I'll do is pause and take questions. Thank you all for your time.
Where did that expert come from that you asked about the analogy?
Right now, it's Pranay.
It's like it's a human.
It's a human, correct. Again, in theory, you can imagine it could be an LLM that's scoring this, blah, blah, blah. Right now, it's a person. Yeah, in the back.
So I'm curious about all these distances. Think about like the early analysis, you have this reduced dynamics, whereas then in the later work, you're saying you're using cosine similarity at one point in the latent space, then you're also averaging. I mean, if you looked at like on manifold distances in the latent space, like what is the actual distance induced by the data?
We're studying this now. So I don't have a good answer for you. We're trying to, basically the philosophy we've taken recently, especially with some of these works, is we were just trying to come up with an existence proof for scaling some of these foundational tools to these like stranger models and more frontier representations. Now that we've seen some signs of life, our mission is to understand a little bit more deeply. So the questions you're asking are precisely some of the ones we're going back to the drawing board.
Do you feel like when you're doing like the OOD avoidance, like potentially you could lose generalization if you stay always in distribution? Like I remember you were mentioning about functional correspondence. Does that like play into this?
Yeah, I mean it's a trade-off, right? Like you're telling your model you can only do exactly what you know. Maybe the hope is that if you have done a really good job of uncertainty quantification, you'll never do something that you don't know. But if your model has learned to generalize, then it knows very certain what's going to happen next. And in fact, in like some toy environments, we saw this to be kind of true. For instance, we saw like, for example, we have like a toy environment with like a Dubin's car vehicle that has to avoid a circular set in the state space. You train the world model this way. You do some uncertainty quantification top the world model. And if you're asking the world model what's going to happen next to predict essentially just free space motion that the model has never seen, oftentimes the model is pretty confident about what's going to happen next in free space. But if you tell it to interact with, let's say, a colored part of the environment it's never seen, it gets really, really uncertain. And that's because it's seen a lot of interactions with like free space. And so it generalizes really well to like other free space. And we're not conservative there. But it really comes down, I think, to how you do the uncertainty quantification.
So when you fine tune on a new object, have you seen cases where forgetting happens on previously correctly sorted objects?
Yeah, in this work.
Yeah, the last part.
Yeah, so we haven't tried fine tuning right now, but I would not be surprised if some of these.
But by finding, I mean, you know, choosing out of the possible trajectories and you kind of.
I see. And so your question is, if you do this retrieval, you do the intervention, does it ever forget how to do the original task well?
Yes.
I think in these toy environments, we haven't seen that, but it could happen if we scale this up a little bit more. This is just like an initial sign of life, yeah. But in these toy environments, we haven't seen that. Yeah.
In the analogy setting, since the human is giving that analogy once, is there a possibility of like learning that mapping now when like by not collecting another demonstration, was just saying like this corresponds to that.
Yes, and in fact, I think if you were to kind of productionize this system, what you would do is you'd probably have some functional correspondence bank that you have acquired over multiple rounds of, let's say, repeatedly interacting with a stakeholder or an end user, and you get deployed with some set of functional correspondences that seem pretty reasonable. You can keep augmenting them, but it lets you alleviate the need for more expert interventions at deployment.